Okay, welcome. My name is Larry Baker. I'm a research professor in the Department of Bioproducts and Biosystems Engineering at the University of Minnesota. And I work on water, mostly as an engineer, work on physical aspects of water and particularly water pollution, and very much in a human context, agriculture and urban issues. This is part of our water-related training, education, and research in the Global South, otherwise known as WATERS. And this is the first of a series of lectures on biophysical considerations for water resilience. I'm going to start, since much of the audience has background in humanities and sociology and this sort of thing. I'm going to start with a little primer on hydrology, water consumption, and hydrologic resilience. Something at the physical side and the social side, coalescing a little bit. Two examples here in the front. This is just a large reservoir. This one happens to be in Arizona, Roosevelt Reservoir. Very common throughout the world, these types of reservoirs in virtually every part of the world now. And the second is a satellite imagery I'll talk about later, where satellites can actually determine the presence and abundance of groundwater throughout the globe now. And we'll come back to both of those. First, some basic hydrologic concepts. All three of these, the next three slides, come from a USGS publication, which is really a pretty good basic source for hydrologic concepts. In the upper part here, we have rainfall coming down on this, it's a mountain range, but wouldn't have to be. We have evaporation coming directly off water surfaces, and also something called evapotranspiration, which is the water that comes off plants as they grow. And typically most of the water that falls on an area with a lot of vegetation, whether it's a crop or a forest, leaves versus evapotranspiration. Some of the water, of course, flows along in rivers. Below that, though, there is an aquifer. In most parts of the world, there's an aquifer. This is typically a rather porous type of soil or substrate. It might be cracked rocks. It might be alluvial gravel. It might be sand or other materials, but generally porous and typically holding a great amount of water. And I'll come back to a point a little bit later. The aquifer and the rivers are often fairly intimately connected. There's often multiple aquifers. This is a confined aquifer that has been between two confining beds, which are sometimes called aquicludes. And there may be another layer below that, and then another unconfined aquifer above it. Unconfined meaning that this may actually, it's not confined completely by impervious layers. This can actually flow into a stream or the other way around. And I'll come back to that in just a moment. This is very important for a couple of reasons. One is we have, human activities have the most connection typically with the unconfined aquifer near the surface. We contaminate those, unfortunately, both in agricultural areas where we have leaching of pesticides and nutrients and stuff, and also in urban areas where we might have leaching of, again, many nutrients and salts and so forth, and industrial contaminants even. Typically, if they're going to get contaminated, these get contaminated first. Then you're forced to drill a deeper well to get to cleaner water, and sometimes you might go down, in some cases, several hundred feet before you reach water that is fairly clean, if indeed you do it at all. I mentioned that rivers and aquifers are connected. As obvious as it may seem, it's often forgotten in the way water is managed. But I'll show two cases here, again from the USGS publication. In this case, the level of the river is slightly below the elevation of the aquifer. This is the level of the water table, the top of the aquifer. This then would be dry or relatively dry soil or parent material. The water comes, lost my cursor, the water comes in and starts to fill the river. So during the summertime, a river may have very little flow. There's no rainfall going on. The only place for the water to come in typically is through the aquifer. Just seeps in along the sides and comes in. So you can have water flowing through streams that with no rainfall or other visible inflows. At times, rivers can go dry because of this. At times, the river goes dry on this side when the waters are flowing. The river is often higher than the water table, in which case the water recharges the aquifer along the way. When rivers go dry, it's when they drain out to the aquifer entirely, and they can become dry for a period of time. And I'll show you an example in a minute here. This is the concept of an effluent-dominated stream. It illustrates a couple of these points. This is near the city of Tucson, Arizona. Upstream of the city, there's a pretty healthy little stream here called the Santa Cruz River. It comes in from Mexico, north to Arizona. But as it moves through the city, there are a lot of wells in the periphery here that suck the water out. I mean, they're all over the place, not necessarily right in these places. And they suck the water out. So by the time the water goes halfway through the city, it's pretty much, the river is pretty much dry, at least during the summertime. At the end of the city, at the other end of the city, some wastewater comes in and it starts to fill the river again. The upstream section is dry, then there's a point here where it enters and it becomes wet again. And that's what we call an effluent-dominated stream. The effluent being the effluent from the wastewater treatment plant. So this is a fairly common situation. I know it occurs in Baghdad. It occurs in many other places around the world. Some water use definitions now. We're going to talk about water withdrawals. Before we were talking about basic hydrology. And that's of two types. One is consumptive and the other is non-consumptive. Again, sometimes gets a little confused when people talk about taking water out of a river or out of an aquifer. The consumptive use means more or less what the word says. The water is consumed by evaporation or becomes an input into manufacturing. Most irrigation water, for example, is lost by evapotranspiration. Goes up into the air and it's no longer available for anything else. Cooling towers for power plants, at least the ones that recirculate the water many times, typically 3 or 4 times, that water is lost by evaporation. In other types of cooling towers, the water is not lost, it just comes through once, it cools in coils, it cools the plant and then goes out the other side with no loss of water, no consumptive loss. Some manufacturing, water comes into the factory and beer goes out. That's essentially a consumptive loss. Water that's drunk is a consumptive loss. On the other hand, much of the water that we withdraw from a river or groundwater is not consumed. Most of what comes into a household is not consumed. I turned my sink on this morning, cleaned some dishes, and the water went into the drain, went back ultimately to the river, through a sewage treatment plant and back to a river. If you flush a toilet, it goes back to the river, essentially, hopefully indirectly. Excess irrigation water, the water that's not evapotranspired, goes back through ditches or infiltrates into the ground, and that becomes non-consumptive use. Agricultural water use, you can illustrate this a little bit. We have the effective irrigation plus effective rainfall coming on the surface. We have evapotranspiration, removing water goes into the air. And then you might have the leftover goes into tailwater that might go into a ditch and then into surface water. And I'll show you a photo of that later. Or into deep irrigation, in which case it recharges groundwater. So we're going to define irrigation efficiency and then talk about that in a minute as the evapotranspiration divided by the amount of water applied. So this is the water applied here, and this is the evapotranspiration. What we call evapotranspiration, or ET, it's a function of the crop type. Some crops transpire more water than others. The temperature, hotter weather typically results in more evapotranspiration than cooler weather. Radiation, when the plants are growing, there's a lot of sun, generally has more evapotranspiration. And wind kind of dries things out, creates more evapotranspiration. And there's equations for predicting this used by hydrologists and such. Some typical irrigation efficiencies. First, I'll show the types of irrigation systems. Here's on the left, a spray irrigation. This is a water spray coming out into, I think this is a vegetable crop. I can't quite tell what. Here is typical furrow irrigation. The water goes between the rows of crops and seeps into the root zone from the sides here and here. And this is drip irrigation, and there are little nozzles that come out and irrigate individual plants. This is probably better on especially on a large scale for irrigating large row crops, things like corn and soybean and stuff like that. And these two are used more for vegetable crops, cabbages and peppers and all that sort of thing. The surface furrow irrigation is the least efficient, 55 to 75%. This is in Arizona, but these are probably all comparative just about anywhere. Precision leveled basins, so it's still furrow irrigation, but before farming, it's all leveled out very, very carefully. That can get up to 84% efficiency. Sprinkler irrigation can be quite variable, 70 to 90%. Drip irrigation with a point source, up to 93%, and drip tape, where basically this is a flat hose kind of thing with little holes perforated in it, that can go up to 95%. So very different use efficiencies in different kinds of irrigation systems. This illustrates the difference between withdrawal and consumption in various parts of the world. In North America, one of the biggest uses of water is for one-time through cooling. So basically the river just comes in through a large pipe, cools the power plant, and then goes back out the other side. That does not use much water. There's very little consumption. There's a huge amount of withdrawal, but not very much consumption. So we have a lot of that. So the consumptive use is really quite small compared to the amount that's withdrawn. We'll go over to China. We have something intermediate. We have a great deal of withdrawal, but the consumption is more of it goes toward irrigation than anything else. So the consumption, this is the part that goes into the evapotranspiration, is really quite large. In Europe, somewhere something in between, and Africa, more consumption due to irrigation and ET. And this shows kind of the same thing, but for the whole globe. And it shows a trend from 1900 to 2025. If we look here, here's agriculture. Great, huge increase in water use, and overall the largest use of water. Now this is globally. And note that we were looking at numbers in the 50 to 90% range. Note that globally you're looking at efficiency. So this is the excuse me, consumption compared with the withdrawal at about 70% or thereabout, varying a little bit through time. But probably 70% is a good round number if you had to use one. For domestic use, remember we said that very little is consumed. What comes into a household, it mostly goes out the other end. And again, globally, very little consumed compared to what is withdrawn. And for industry, a great deal, again, very little consumption, a great deal of one-time through use for electrical power, which is shown in this, which dominates these withdrawal bars. So very little consumption, a great deal of withdrawal. Now, with regard to using water, this is an estimate of the absolute minimum that's needed for human use. About 5 liters for drinking, a little bit for sanitation, bathing, and food preparation. Peter Gleek of the Pacific Institute estimated these numbers and suggested a minimum amount of water for human survival is about 50 liters per day. Now, we have a lot of other uses for water. This is a little diagram that I've made up, built a little bit around the Maslow's triangle or Maslow's hierarchy of human needs, translated into a hydrologic perspective. So it's a hydrologic version of Maslow's triangle. We start with drinking water, bathing in laundry. Here we come up to our 50 liters per day here. Now we have some choices. These aren't so much choices down here, really. But how much water do we need for production? If you have in a city a meat production facility requires a lot of water. Any sort of beverage manufacturer requires a lot of water. Most industries require some degree of water, and that has to be allocated. Probably fairly low on the production on the Maslow's triangle, because you have to produce something in order to make money, which then you use to buy things like, moving up your system here, a flush toilet, perhaps, a washing machine, perhaps. And my observation has been in some parts of the world, the washing machine comes before the flush toilet, and other parts of the world, the flush toilet comes first, and the washing machine is still, is not there yet. It's still hand washing. Moving way up, as houses get bigger and people get richer, second flush toilet, turf irrigation is kind of a luxury to create the paradise of our backyards. And then finally, a swimming pool. I used to live in Arizona. Floating on a air mattress in the swimming pool with a beer, I guess, is the top of the Maslow's triangle of Maslow's hierarchy of needs relative to water. Somewhat tongue-in-cheek, but there's also some validity to this. We are facing growing pressures on the global water situation. First, and I'll show slides of each one of these. First, there are growing urban populations in the global south. We have much of that population growing in semi-organized area, these para-urban areas that are sometimes as large as the core area or the organized area itself. There's growing wealth around the world, particularly at the lower end. Lower income end is increasing quite rapidly. This is leading to increased per capita water use. And there are increasing droughts, largely the result of climate change. So let's look at each of those. This is the urban population, and notice that the growth in the northern hemisphere, in the United States, in Europe, almost all of the northern hemisphere is very low, less than 3% per year, and in most cases 1% per year. The high growth is occurring either in parts of India, parts of China, the Middle East for sure, and particularly the red, if you look at the red, the 5% or more growth in parts of Africa. So much of the impact of water stress is going to be in these areas, not so much, as much at least, in the northern temperate areas. Also, much of this growth is occurring in these para-urban areas. This is an unorganized area near or around Ouagadougou, Burkina Faso. There's a little bit of infrastructure here. There's some power lines. There is, I don't know in this particular street, but down about a quarter mile, there is a community water supply. There's no piped water going into houses in this kind of area. There's no sanitation, organized sanitation in this kind of area. And there's certainly no sewage treatment or anything like that in this kind of area. And these surround entire urban areas throughout most of the global south. And they're more vulnerable to water stress than more organized parts of the city. I said that the water use is going to increase, or it is increasing as we go through time. But here is, I'll show you the domestic first. If you look at the per capita income on a parity basis versus the water use, it typically goes up. The exception here are a couple of European countries, Germany, the Netherlands, and I believe France, that have really made big efforts to conserve water. But generally speaking, the richer you are, the more water you use. And that's true even at the in fact, the relationship's more precise at the lower end than at the higher end. The same is also true for total water use in a country. Now that includes agricultural water use. You get increasing use as you increase your income. So we're getting wealthier, we eat more meat, we use more domestic water. The meat production requires more corn, more agriculture, more irrigation, and we increase our overall water consumption. The next aspect of this is that droughts are likely to get worse. This map shows droughts throughout the world. The red zones, I guess you can focus on those, are where droughts are the most severe. Okay, Central China, Middle East, Northern Africa, and so forth. Now, I want to show you how this is changing. So you're going to see another overlay on this. This is 2000 to 2009. Now watch the red as we fade in here. Now we're getting redder, 2030 to 2039. We're getting much expanded areas of red, including the United States, the western part of the United States, and much of South America. And now I'm going to go forward one more time to 2060 to 2069, and now you can see that much of the world is red. It has more likelihood of drought in the future. These are substantially, I'll walk this back, okay, backward, and then forward again, so you can get the sense of this. And then forward. Redder and redder and redder. Droughts will get worse in the future, so we have to be better prepared for them. And this is kind of summarizes the situation around the world. Where are droughts going to be worse? Actually, the western U.S., Los Angeles, and around there. Much of the coastal areas in South America. But look at India, the Middle East, Africa, the red dots, where you're going to have the worst drought impacts. It's going to be very bad. It's going to occur largely in urban areas, and we're going to have to learn to deal with it. So some of these thoughts have triggered me to think about resilience and robustness in relation to drought. This is in a book chapter that it's kind of in late review and final refinement, I got thinking about this when I was in Africa briefly, and I'm thinking about the impact of a drought. And this can be per capita income, it could be health, it could be disease, and other things. For example, if one of your measures of impact might be the occurrence of waterborne diseases or deaths from waterborne diseases, and that might go up as a drought proceeds. So here's the situation before a drought, during a drought, and after a drought. Okay, I'll start with the 4 different city types. A is neither robust nor resilient. Now, what do I mean by that? The best analogy I've seen of this is a book chapter. It talks about a willow tree and an oak tree. An oak tree is much stronger. It's a very hard wood. The trees grow quite tall, and it will take a lot of wind. 50-mile-an-hour wind, 80-mile-an-hour wind. It'll stand up straight. But then finally, it breaks. When it breaks, it snaps. Okay, and then it's dead. There's no way you can bring that tree back up again. So it's robust, but it's not resilient. A willow tree, on the other hand, has leaves kind of hang down like this, typically near a stream. You can wave, you can move the branches around. When the wind blows, the branches all go to the side, and I think a strong enough wind would even go probably nearly horizontal. But then when the wind stops, the limbs go back down, and the tree is right back where it was. So it's not robust. It moves during a wind, but it's very resilient. It just comes back to its original condition very easily and survives the windstorm. So you can think of cities in terms of both robustness and resilience. So the first city is neither robust nor resilient. They're utterly unprepared. Things are going along, a drought hits. They may have no redundant water supply. Maybe they're coming from one stream, for example, but have no reservoirs on that stream to dam the water, to hold the water. They may have only very shallow wells going to their aquifers, and they maybe have very limited water in the aquifer. So they decline very rapidly during a drought. Perhaps people move away. Perhaps there's more waterborne diseases as people move to lower and lower quality sources of water. The economy fails because there's not enough water to do production and so forth. And the city may never come back. And there are historical examples of this. The Mayan civilization in Mexico, the Hohokam in Arizona, the Angkor civilization in what is now Cambodia, all declined during or after a drought. I think it's probably safe to say that an area is already declining. The drought tips it over the edge. A drought itself is probably not going to destroy a very robust civilization, but when things are in a period of deterioration, it might well deal the death blow, so to speak. City B is robust, but it's not robust necessarily, but it's quite resilient. It may come down, maybe they didn't have a reservoir, maybe they didn't have enough wells, but they maybe pooled their resources, maybe they were a bit wealthier. They might create new laws for water allocation and so forth. They pull together and eventually climb back out of this and go back to their regular previous state. So it's not necessarily robust, it suffered a lot, but it's resilient in that it came back. City City B, I forgot about that, is robust but not resilient. So they may have had a nice reservoir, maybe it holds 2 or 3 years of water, and the drought hits, it's very dry, very hot, no rain. And they say, well, we still have our reservoir. And the first year they still do. And there's absolutely no effect. It's quite robust. Everything goes along quite normally. Goes into the second year, maybe a little bit of concern. The water levels are going down, but not so much that they get terribly concerned. And then it turns out it'll drought last 5 years, and now where they were resilient, they were bouncing around near normal conditions. Now they were robust. Now the robustness runs out, it snaps like an oak tree, and the city declines like this. And D then finally is, C then is robust and resilient. It's well prepared. Maybe it has 2 reservoirs on different watersheds that pipe into a city. Maybe it has, maybe they've dug deeper wells so they're not quite as reliant on the shallow groundwater. Maybe they enact laws that prevent people from overusing water, and so forth. And they really don't decline very much. Things probably move downhill a little bit, but then not terribly, and they come back to right where they were. I think this is where you want to be. This is certainly where you don't want to be. And this raises the issue of the definition of a drought. Normally we think about hydraulic drought or hydrologic drought, meaning either less rainfall or less water flow coming into an area. But really, we're starting to rethink this as a socio-ecological situation. All of these cities, hypothetically, experienced the same drought. Some survived and did nicely, some didn't. And so the idea of a drought, as we think about management, it's as much a governance issue, in relation to things like transparency of data, accessibility of data, the way resources are allocated to bring water to all the people or only a few of the people, and so forth. So we can rethink this a little bit, and certainly the way we respond to that hydrologic drought has a large influence there is how the social system is set up to respond to that. So good topics for discussion if you're in a classroom setting. In ways, so far I've been pretty depressing about where things are going. There's a flip side to this. The technology, the transparency, equity, these things can increase. We have a growing ability to acquire, store, process, and share data, which can create transparency. It doesn't necessarily, if people are blocking your internet connection, but it can, and it creates accountability on the other side of that. For example, imagine a well monitoring system in a fairly poor country where you don't have automatic well measurement and things like that. You might put a ping pong ball or even a piece of wood on a stick, or on a string, measure out the string so you know how long it is, and drop it into a well, determine when the tennis ball or the stick hits the water surface, and then measure how far that is, and then transmit that information on a cell phone to a data processing facility. A data processing facility can be anywhere on the globe. You could have data coming in from a community in Africa going to a data processing facility in India or Russia or the United States or anywhere else. You could then, let's say in this particular situation, you then take all of the data that you're collecting in an area, whether that's a community or region or even a continent, and map that out and then send back to the cell phone all that information back. So the individual in a village who was monitoring their well and providing one data point now gets to see the map of what all the water elevations are in the region, or again, the whole country even, and then use that information to manage water or to demand that other people manage water better. You can no longer say, in some circumstances, governments have actually lied about droughts. Apparently this happened in South Africa once in the 1960s. They couldn't even accept that there was a drought that was visible through groundwater decline because nobody could see, except the government officials, nobody else could see the data. Well, now you can start to see data. It's pretty hard to keep it completely insulated. And also, even if you have a good, transparent, uncorrupt system, simply the capacity to be able to do this and map things out and provide feedback gives you a really improved ability to manage water over time. And I've suggested in this book chapter that social scientists often are disparaging of engineers, and I understand that, but on the other hand, using the technology in the context of creating better governance systems has a tremendous amount of potential in water management. I'll give you a quick example. This is actually goes back to the 1990s, but it's an example of what I'm talking about. This is again in Arizona. There's a network of these MET stations, meteorological stations. So these measure, there's a wind meter and anemometer there. They measure temperature, they measure humidity, I think down here. And that's measured at 25 sites around Arizona. The data goes into a central facility. They compute the evapotranspiration for each crop, cotton, oranges, whatever. And they do it day by day. So at the end of the week, a farmer on his computer can now go to the internet and see how much water was used by his crop, his cotton crop, for, say, the week. And then can make a decision that it is time to irrigate. I need to irrigate by 1 inch or 2 inch or 3 inches or whatever it is. and irrigate very precisely. It's not guesswork anymore. It really becomes quite precise. Now, you can today skip the computer. You go directly to a cell phone and do that. But the idea, this is not a particularly expensive setup. You can do this in many, many parts of the world and manage water in much more precise ways than you could just a while ago. The other point on data utilization, sometimes people have said to me, well, you can't do that in other parts of the world. Well, they were probably thinking what happened back in 2002 when there were very few cell phones in most of Africa, for example. But now look at this, even Uganda, Tanzania, 70% cell phone utilization, Ghana, 83%. And remember, cell phones can be passed around, so many more than 65% of the people have actually access to this kind of information. And we're converging on a point where it looks like the whole world is going to be 90% saturated with cell phones. That means every individual potentially has access to hydrologic information that they would not have otherwise had. And that, I think, is a very, very major point as we think about how water might be managed in the future. Particularly with respect to the governance systems. What does this really mean in a social science perspective? There's on the flip side, we're talking about local water measurement and stuff. We can also map out the whole world. This is brand new. This is the GRACE satellite system, and the only part of that acronym I can remember is gravity. It's satellite imagery based on gravity, and the way it works is that the water content of the groundwater changes the density of the mass, and therefore, and the satellite measures that change in gravity. The Earth has more or less pull depending on where you're at and what the situation is. But water does affect that, and NASA, the National Atmospheric National Aeronautics and Space Administration, has mapped out the whole globe. These are shown in big clusters here, but this can be done on a very fine scale. A colleague of mine has a map just of Minnesota and is trying to look at where the groundwater is declining and where it's staying stable and where it might be increasing. And you can do that anywhere in the world now. This just came out, first papers, very recently, past couple of years. Again, you could map out this groundwater levels, and you can transmit this to any point in the world, any individual, any cell phone in the world. I'm not sure that is happening quite yet, but it very, very soon will. So we have eyes now into our environment that we didn't have way back in 2000 and such. So in summary, the hydrologic cycle, watersheds gain water by precipitation, natural inflows, and human importation. It's lost by evapotranspiration and outflows from rivers and aquifers. Surface and groundwater are connected. Agriculture is the biggest use of water globally, and most of that water is consumed. The largest industrial use is cooling water for power plants, and that's mostly non-consumptive once through, although it can be consumptive if it's a recycling type of cooling tower. Drought hazards are increasing. This is very important for anybody thinking about water. Growing population in high hazard areas, climate warming, increasing per capita wealth, and so forth are making the situation generally worse. The resilience of cities to drought depends on the social as well as the hydrologic conditions, so we can think about social ecological drought, not just a meteorological drought. And finally, and very importantly, technological advances are rapidly improving the potential for building drought resilience in the global south. Thank you.